The question we would like to answer now is it possible to make a generic dynamic programming solver? And this will be exactly the topic of the project that you will solve for the first assignment. So the answer is yes, of course, we can make a dynamic programming technology approach quite generic for solving any kind of dynamic program, simply because any kind of dynamic program, one way or the other, is aimed at solving a longest path problem in a directed acyclic graph, longest or shortest path. So this is one such example. So you have a graph and you see that it is rooted starting at this node that we call the root node, and we have the sink node there, and we have a weight on every edge of this graph. And the goal is to find the longest path that will join the root node to here, the sink node T. And the goal is to make this in polynomial time, and you can convince yourself that on this specific instance, the longest path is depicted here with the blue edges here. And the longest path here has a total weight of 28. This problem in general is a hard problem, NP hard, but because this graph has no cycle, the problem is as easy as the shortest path problem. So let's see how to retrieve the longest path problem in a DAG. The way you could solve that problem, I will illustrate this on a numerical example, is you do it bottom up. So you will start from there and gradually you will attach the longest path from the current node to the tail, to the sink node T. So clearly from that node you have no other choice than going there. So that's 3 for the longest, for that one that's 4, and that one that's 2. And then it becomes a little bit more interesting. So which direction should we choose if we are here in node C2 and we are trying to reach T in the longest possible way? So we will simply take the maximum between the two. So that will be the maximum between 3 plus 7 and the maximum between 4 plus 8. Okay, and in that case the maximum is going in that direction. So 4 plus 8 is equal to 12. You do that for every node of this current layer. Okay, and then you do that from that layer, and then from that layer, and then that layer. So it means that the total time complexity that is required here is to visit every edge exactly once, simply because you simply need to compute, you can compute in almost constant time the value that you have to attribute to every node by considering just the outgoing edges and the value that you have previously computed. So you will really proceed bottom up from the node T up to the root node R, and you will do that in linear time in the number of edges to retrieve the longest path. Okay, and so as I said, any dynamic program can be transformed into finding the longest path problem in a graph. And so the framework that we will implement is composed of 3 classes. There will be the states, and the states are exactly the node that I represent here, okay, on this graph. These are the states, and we have the transition. These are the edges, and they are directed, and they represent the edges on this dynamic acyclic graph. Then we will need a model class that will just take the responsibility of generating the successors of a node. And so the successors really mean from the node B2 you will have to generate the successors, so C1 for instance and C3. Okay, that will be the model that will be in charge of the generation of the successor nodes. And for the solving algorithm, we will use a hash table, and this hash table will store every node here of the graph, and so implicitly we will be able to retrieve if a node already has been generated. So for instance, from B1 you would generate C2 clearly because that's a successor, but then you will use the hash table to realize that the successor of B3 has already been generated, and this one will be stored inside this hash map there that we call the table. And so the hash map will be a map from the states to the best objective value for the state. So the longest path from the root node to that specific node inside the table, and the node, as I just said, is represented as a state. And so because it's a hash map, a state must be hashable. And that's the abstract class that you need to implement for your problem in order to have a state. You will need to implement the hash code. And so the hash code here will be used to make sure that 2 nodes are considered equals by the map. Okay, so you need to implement the hash code. And for that, for the knapsack problem, for instance, if you remember, the state that we need to store is just composed of two integers. Is first the index, that is the corresponding item that you have just included or not inside the knapsack, and the remaining capacity, so the leftover capacity inside the knapsack. Okay, and so that's the state here that you have for solving the knapsack problem. And to compute the hash, well, we could do it ourselves, but rely here on the hash function that is available in objects that is here. Okay, so you can compute the hash of a set of objects here, and we give here the successive integers that compose our state, so the index of the item and the corresponding leftover, so the corresponding capacity, remaining capacity. Okay, and we rely on this hash function that is available in Java. But we could have implemented the formula ourselves. For instance, you could have done the item times the maximum capacity plus the capacity. Okay, that would be also a valid hash table function. Then in terms of transition, so the class transition, the Java describes one edge in the graph. You have nothing to implement there. Okay, that's already done for you. Okay, it's just a class that will remember for you the decision. So the value that so in that case for the knapsack is 0 or 1 if you take or not the edge, and that's the corresponding weight of the edge. So the value that you have on the edge, that's the corresponding weight of the item for the knapsack problem. So nothing to implement for the transition. For the model itself, yes, you need to implement that class. So first you need to say if a state is considered as a base case. So if you have already reached the sync node or not. This is exactly what this method means. Okay, that one is the same. So that's the base case value, but most of the time the base case value is 0. Then you have something to generate the root state or retrieve the root state. And then you have this very important function that just generates for you, starting from that node as, it will generate the list of outgoing nodes. So the list of the transitions here that are going out of that node. And that allows you, because the transition will remember for you the successor state, okay? And so this one gives you access to the set of nodes reachable from that given state S. And so that's exactly a problem-specific method that you need to implement. And then you have a Boolean method here that you should return true or false if it's a maximization or a minimization problem. Okay, the most important class now, of course there is a state, but that one we already have seen it, is the implementation of the model. And so the model is a generic class and you need to give it a type, and this type here is the knapsack state. Okay, we say that we implement a model that is operating on knapsack states. We have two instance variables, one for the root and one for the instance of the problem, that will just be here an object that stores the input data of the problem, so the weights and the indices and the values attributed to each item. Is base case, you just need to check if you have already reached the last index. Okay, if you have reached the last index, or if the remaining capacity is 0, then it's a base case. Okay, then you stop. You don't want to generate the successors going out of that node. Then that's the important one. So the outgoing transition starting from this one. If you remember, for the knapsack we have two transitions. Okay, we have the transition that gives 0. Because it just means that you do not select the item, and there is the transition 1 if you do select the item. So it's always a binary node. In that case, you always have a 0 transition and a 1 transition, and so that is reflected by this value on the transition. Let me see. Yeah, that one. So that one that you see here, that one and that one, it means I take the decision 0 to say that I did not select it, and that's decision 1 to say I do select the item. And the weight, if you do not select it, is 0, and the weight, if you select this corresponding item, you just retrieve it from the data. You say instance.value at this given index. Okay, and you retrieve, and that's the weight of the transition there. And of course, you need to create the new state. Okay, you need to create the new state. And the state will be, the knapsack state takes two different things. It's composed of the next index of the item. So that one, in both cases, you just move to the next one. So if you were at index 1, you move to index 2, okay? And that's the next layer of your dynamic acyclic graph. So you just do +1 in both cases. And then you need to compute what is the remaining capacity inside the knapsack. So if you do not select the item, the remaining capacity is completely unchanged. Otherwise, you need to decrease the remaining capacity by the corresponding weight of the item that you just have included inside the knapsack. And that's it. You return these two transitions here that you have added inside the list, the linked list. And then there is the dynamic program. So that's really the core of the algorithm. Okay, you need to compute a solution. So you need to return a solution there, starting from the model that is provided here in argument. That one is a to-do, okay? It's not implemented for you, but it's quite easy. What you need to implement there is the algorithm that I have described here on this example to retrieve the longest path, okay? And of course, you will store each of the states inside the knapsack. But here, I did it bottom-up. What you will need to do is to do it top-down, and you need to implement a recursive procedure for that. But that's exactly the same. And every time you find an optimum here, don't forget to put it inside the map. And if it's already available inside the map, you can retrieve that from the hash of the state. If it's already there, you do not rerun the recursion, of course. You just return the value that is already stored inside the map. Okay? But that's part of the exercise, so you just formulate the recursive code here to retrieve the longest path and the solution. And the solution object is really a linked list that takes here that stores every decision for every decision decision variables, one at a time. But in your algorithm here, probably what you will do is have a recursive procedure that is able to retrieve the optimal objective for every node. Then it's another thing that you need to do to recompute the solution from there. There is one easy way to do it, is just this way. So you start from the root node. So assuming that you have already all the best values that are stored inside the map because of the recursive procedure that you have implemented, then it's easy to retrieve the longest path. You just need to replay everything from the root to the thing. And for that, the longest path is always the one that corresponds to the best decision. So here you know that the optimum is 28, and you have in the successor 26, 26, 27. So you can get the maximum between 27 plus 1, 26 plus 1, 26 plus 1. So it's 28 minus 2, 28 minus 1. Okay, and you see that both here are equally good, right? Because both decisions here would lead 26 plus 2 on 27 plus 1 would lead to 28. So let's assume that that's this one. So you greedily access to that one, and you do the same from there, okay? So you take the maximum between 26 minus 4 and 26 minus 3. And the maximum is in that direction. So you proceed with that edge and you continue like that. And you retrieve like that the longest path, starting from the optimum value that are stored inside the hash table. And that's it. So what you need to do is to instantiate this framework that is provided for you and that you need to complete with your own implementation of the algorithm for retrieving the longest path. You need to instantiate this framework for the traveling salesman problem. And for the traveling salesman problem, you need to find a way to define what is the state here. And the state, just to give you a hint of what it could be, think about all the remaining cities that remain to be visited by the traveler, okay? And probably you can store that inside a kind of hash set, okay? You can store the remaining cities that need to be visited inside a kind of hash set, and you can store inside the nodes, the value of the longest path up to that node, okay? Because whatever the set of cities that you have visited, if two different orders gives you exactly the same distance, it means that you are exactly in the same state. Okay, good luck for the assignment. This finishes our lecture on dynamic programming.